Now, classical optimization problems are not the only situation which can be mapped to the problem of finding the ground state of an assembly of qubits. Also, problems in quantum chemistry can be mapped to that kind of problem. In quantum chemistry, you often want to understand properties of molecules, electrical, optical, chemical properties of molecules. And a theoretical study of such molecules always involves determining the electronic ground state of a molecule. You later then also need excited states, but it always starts with the determination of the ground state of the molecule. This is classically a hard problem because finding the ground state of a Hamiltonian means that you have to diagonalize, find the spectrum and the associated eigenstates of a Hamiltonian. Now, when you have a matrix representation, then this problem scales, or the resources that you need scale with the dimension of the Hilbert space. And the dimension of the Hilbert space in turn scales exponentially with the number of electrons. So very quickly, when you have more complicated molecules with many electrons, the complexity for in the classical case grows exponentially. Before we talk about how this can be tackled more efficiently with a quantum computer, let's consider a few basic physical insights about this, this problem. Let's define an orthonormal basis of single electron states. These are also called orbitals. So if we consider a single electron, then a single electron can be described in a Hilbert space spanned by these orbitals, these orthonormal basis states. A very fundamental property of quantum theory is the fact that quantum particles are indistinguishable. So if I have two electrons and say one electron is in the orbital 1 and the other electron is in the orbital 2, then it does not make sense to say electron A is in orbital 1 and electron B is in orbital 2. Because the labeling of the electrons is arbitrary and the electrons are indistinguishable. There's no difference. Electron B is in orbital 1 and electron A is in orbital 2. So the labeling doesn't make sense. All you can say is one of the electrons is in orbital 1 and the other is in orbital 2. Doesn't make sense to label them. This means that when you consider many electron basis states, you don't write them in the form, say, orbital 1 tensor orbital 2, meaning the first electron is in orbital 1, the second electron is in orbital 2, because this would imply a distinguishability of the two electrons. Rather, you write many electron basis states in this form of a ket where you denote the number of electrons occupying orbital 1, the number of electrons occupying orbital 2, and so on. Yeah, so you only consider the number of electrons in a given orbital, but not their labels. I'm sure you're familiar with that from statistical mechanics. Yeah. And then there's the fundamental Pauli principle for fermions, and hence in particular for electrons, that each orbital can only be occupied at most once. So every orbital is either empty or occupied with a single electron. That's the Pauli principle. And here's the basic idea how such a quantum chemistry problem of finding the many electron ground state can be mapped to a problem regarding qubits, and then it becomes manageable for a quantum algorithm. The basic idea here is to say that every orbital is either empty or occupied. And then you say every orbital corresponds to a qubit. And if the orbital is empty, then the corresponding qubit is in basis state 0. If the orbital is occupied, then the corresponding qubit is in basis state 1. Yeah, so the basis states 0 and 1 have the meaning empty or occupied for the orbitals. In practical applications, you always make the assumption that there is a rather limited, and in any case finite, number of orbitals which are relevant to the problem at hand. Yeah? So to make it manageable, you limit, and you always want to calculate the ground state up to some finite, good enough accuracy. So you limit yourself to a finite number of orbitals, and then you do this mapping from orbitals to qubits. And as in the classical optimization problem, you can map the many electron Hamiltonian to a many qubit Hamiltonian. Only that this is generally not as straightforward as it was in the max cut case. There exists transformations. One is called the Jordan-Wigner transformation, and others that allow you to map in a systematic fashion many electron Hamiltonians to many qubit Hamiltonians. And I'm not going to go into the technicalities of this transformation. I just wanted to show you the basic idea that in principle you can map such a quantum chemistry problem to a problem for qubits, and that can be handled with a quantum algorithm. And this is the reason why you may have heard that one of the most promising applications of quantum computation, also in the nearer term, is simulation of molecules and materials because of this mapping. What we discussed today is that both classical optimization problems, or a certain class of classical optimization problems, and problems from quantum chemistry, like this one here, can be mapped to qubit problems, and in particular finding the ground state of a many qubit Hamiltonian. And next week we will start from this premise, that our problem is finding the ground state of a many qubit Hamiltonian, and I will show you an algorithm that does that.